Okay. We're gonna do some more U-substitution examples. Excuse me. We could, of course, with any of these sections, do dozens and dozens, if not hundreds, of different examples. But I don't want to make, 130 hours worth of videos, so we'll try to keep it reasonable. Do something a little different each time. So what I want to do in this one is look at two different options for U's that we haven't talked about yet. So I've added them to the list. The first concept is if you have some sort of a fraction set up, some sort of an integral with a fraction, and it doesn't sort of clearly fit into one of the obvious, like arc sine, arctan, arcsecant, one of those inverse trig setups. Those are like very, very specific. So if it's not that, if it's sort of just a generic fraction, and it's also not able to be sort of split apart and reduced like we did in one of the earlier videos. So if it's not one of those things, right, not something that we could have already solved for is sort of a one-step kind of process. A good way to approach it as U-substitution is try the denominator as your U. So pick whatever it is that's in the bottom and start with that as your U, and then start going through the U-sub process. Another option for U's, this is a little bit less common, but another good option for U is if you have a natural log of x somewhere in your integral. You won't see that tons and tons, right? If we think of like, how did you even end up with natural log of x as a derivative? There's not really an obvious way, but say you do have an integral that uses a natural log of x. Using natural log as your U can be a good strategy. So literally just let the U equal natural log of x and then sort of continue trying to solve the problem from there. So let's start looking at the examples. I had actually started making this video before and it got cut off about 2/3 of the way through, which was pretty frustrating. So I have a lot of this written out already. I'm just going to sort of talk us through it, and then I'll finish up, right, sort of writing the final solutions here. So let's start with a fraction one. What I have is the integral of x over 4x squared plus 3 dx. So this is exactly what we were talking about, right? This is a sort of fraction, right? A rational expression. It won't split. If this was flipped upside down and it was the x on the bottom and it was 4x squared plus 3 on top, you could break it apart and then reduce it and sort of rewrite it and deal with it as, in terms of just like power rule stuff. It's not, right? It has more action on the bottom. There's not really a great way to clean it up. So let's let the U equal whatever's on the bottom. Let U equal 4x squared plus 3. Of course, when we do that, we'll take a derivative, right? So take a derivative of your U. The derivative here would just be 8x, right? Plus 0, so the derivative is 8x. Do our sort of bait and switch, kind of cross multiply, bring this around. So the dx that we would sub in would be du divided by 8x. If I start to do my substitutions back over here, what we have is sort of x on top, right? The bottom is our u, and then our dx, right, is du over 8 times x. So what happens here are these two x's, right? And this is sort of generically what we want to have happen in these U substitution problems, right? We sort of start to sub in for the u's, and then any of the leftover x terms start to cancel each other out. So x and x get canceled here. So this is really, right, what we're dealing with. We could write it as 1 over 8 times 1 over u du. The 8 is still here, right? Nothing's happening here. It's in the denominator, so we could just write it as a 1/8. So that just is a generic constant that's out in front. What am I going to do with 1 over u? Well, that is, in theory, u to the minus 1, but I suppose more usefully, it's going to be the derivative for a natural log, right? So whenever I see 1 over u, I'm going to think reverse engineer it back to natural log. It's got the absolutes over it. That's important. So this is 1 over 8 times the natural log of the absolute value of u. plus big C, right? This is just sort of a generic one. And then that's my integration, right? All I need to do from there is sort of sub back in my original u, which was the 4x squared plus 3. So sub it back in my parentheses, and that's what I've got. Generically speaking, right, this kind of strategy, this fraction strategy where we're using the denominator as our u, it works to give us this natural log type setup, right? When we talked about natural log derivatives and sort of did that review, if you have a chain rule, you kind of get this 1 over, when you're doing a natural log of some function, you get kind of 1 over the function times the derivative. And we had said, if you kind of rewrite that, it ends up looking like the derivative over the original. So that's kind of the form that we have here, right? It's not perfect, right? We're kind of missing what would be this 8 that's sort of not showing up here. But that's okay, right? Just different coefficients, different constant values. We can really move around without too much issue. So think of that as a strategy. That's a good way to start if you have some sort of fraction like that. The other example that I said, right, is what if we have some sort of function, an integral that has natural log as a part of it. So in this case, the natural log of x divided by x dx. This is an interesting one because you actually have, in theory, these sort of two different strategies bumping up against each other, right? Try to let the denominator equal u, or sort of try u equals natural log of x. So let's try the denominator thing first. I just want to sort of show you guys, what this would look like, how this would go if we did pick the denominator as u. I'll sort of tell you right off the bat, this is, wrong is maybe the not the best word for it, but this is not going to work. This is going to be kind of a swing and a miss. If we let u equal x, just straight from the denominator, then the derivative, right, the du dx would be 1, so then dx and du would essentially be in sync, right, would be the same thing. If I start to sub this in, right, I've got the integral, natural log x, over u du, this just like isn't doing anything for me. I mean, I guess in theory, I could call this natural log u over u du, but then like, I didn't actually even like change anything. There's no way for me to cancel out this natural log. This is just like not gonna clean it up. So that's no good, but like any good sort of learning experience, we kind of try something out, it doesn't work, so we try something new. So let's do the other thing, which is let's let u equal the natural log of x. So if I do that, right, the derivative would be 1 over x, and then I can do a sort of cross multiply, right, and I'm going to end up with x times du equals the dx. So I get my substitutions here and here, and what starts to happen if I sub those things in, right, so natural log of x is my u, so that's my numerator, right, so u on top, x is on the bottom, right, and then dx becomes x times du. And so what happens here that's much, much, much better than what we were trying to do before is these two x's, of course, right? So what I have here is x and x. Those guys will cancel each other out, right? The x's are gonna cancel. And so I'm left with, in theory, sort of the simplest of all possible integrals, which is just the integral of u du, right? Literally just like 1 u. If I do power rule, that's going to become, right, u to the 2 over 2 plus big C. And so this is interesting, right? So that means the u was the natural log of x, right, kind of as a quantity squared, divided by 2 plus C. So I'm doing a kind of power rule thing, but what's underneath there, right, is the natural log of x. The actual sort of u function is natural log x. So you have this sort of natural log raised to a power. If we think about what would have happened here, 2 times, right, natural log to the 1, 2 over 2 is that, times the derivative, right, from a chain rule of natural log x, the derivative would be 1 over x. So you get this kind of log x to the 1 over x, which is sort of where we started. So a pretty interesting derivative, a pretty interesting antiderivative. And the key, as with all of these, is if you can just pick the right u, if you can kind of get started, right, sort of make the right first step, in all these problems, everything else should kind of just like fall into place and work smoothly. In between videos, I discovered the marble machines or whatever that I was trying to muddle through an explanation. Those are called Rube Goldberg machines, right? If you ever seen like Pee-wee's Big Adventure, right? Pee-wee Herman has, you know, this kind of a machine set up to make his breakfast in the morning, right? So I don't know that anybody else would say U-substitution is like a Rube Goldberg machine, but in as much as you just need to have everything kind of set up, it's all about the setups, and once you sort of make that sort of good first move, the right first move, everything else kind of falls into place, and it should just sort of flow naturally, right? So in that way, it's kind of like a Rube Goldberg machine. I don't know. Maybe you're just knocking over dominoes. Anyways, that's a couple sort of natural log type examples, right? So with sort of a natural log style antiderivative, or also actually with an integral that contains a natural log. So both are things that can come up. You won't maybe see this tons and tons. It's a more special case, but you know, just as an example, compared with the first one, these fractions you'll see probably more often. Anyway, more in the next video.